In this video, we'll be looking at differentiation. So, differentiation is the process of finding the gradient function of a function itself. And this can be used to find the gradients of lines at certain points of a graph. So, for rational numbers, dy by dx, otherwise that's the differential or the derivative of a polynomial in this case, will equal polynomial's original power times by any constant it may have, times to the power of its number minus 1. So, when differentiating the process, if we zoom into a graph, for example at x squared, you find the gradient by looking at 2 points. If you zoom in, you find that the points actually cross the axes, and actually this isn't a perfect gradient at that value. So we use something known as the limiting process, denoted with delta x, which means a small change in x, and we can use this to find, well, the gradient of a function, because as you decrease the size of this, you actually get to the point where you actually converge onto a point where the graph's gradient is what you want, basically, at that exact point. So let's try and do it from first principles. So let's do dy by dx of x squared from first principles. So you want to take, that's meant to be delta, you want to take the limit of this, and you want to get 0.1. So for example, let's just call this point, oh no, we don't need to actually. You just say it's x plus delta x squared minus x squared over x plus delta x minus x. So this, the limiting process is always happening, and for this, that is x squared plus 2x delta x plus delta x squared minus x squared, and these x's cancel out, so it's just over delta x. So I'm carrying on this limiting process. These x squareds cancel out as well, so it's just 2x delta x plus delta x squared over delta x. So you can cancel these. Equals the limit delta x approaching 0 of 2x plus delta x. And as this approaches 0, as delta x approaches 0, the gradient just equals 2x. I'd also like to show the proof of differentiation, well, the equation of differentiation, as one previously shown. This is assuming this time that there are positive powers only. So let's do it. Let's do it from first principles again. So we're going to take the classic thing, limiting process with delta x approaching 0, and it's going to be a to the power of x, so the function will be y equals a to the power of n, not x, sorry, a to the power of n. Okay, and so yeah, let's do this. apologies. I'll just rub that out quickly. Yeah, so does AX plus delta x, actually take the a out, to the power of n minus a x to the power of n, and this is over delta x, as previously shown it was x plus delta x minus x, so you just, you know, sort of get rid of it in the long run. Okay, so this is also using a bit of binomial here, because we're going to use the binomial formula to work out the different stages of x and stuff. So the first term is x to the power of n. This is plus n choose 1 of x to the power of n minus 1 delta x plus n choose 2 of x to the power n minus 2 delta x squared, and then this carries on, minus ax to the power of n, and it's all over delta x. That does not look good. Okay. Okay, so you can see this, you know, there's nothing here. This will actually be n, and this is, well, this you'll see cancel with each other out soon. So, let's do that again. That's x to the power of n plus n x to the power of n minus 1 delta x, and now you will be able to see that the rest cancel out, hopefully. So this is, oh, looks like it's 2. So this cancels out, a to the power of x minus n. A doesn't actually get to cancel out for everything else. It does here, because these are minused away from each other. And delta x here cancels out with that, and this one gets rid of there. So this is equal to nx to the power of n minus 1 plus n choose 2 delta x, and so on. And due to this limiting process, the gradient function is just n. Oh, apologies, there's actually an a as well. Just missed that out. But yeah, nax to the power of n minus 1. Lastly, in this video, I'd like to show you an application of differentiation. So there is a question here with two parts, A and B. For the first part, it says there's an open cylindrical waste paper bin of radius r centimeters, and it has a capacity of v centimeters cubed. It has a surface area of 5,000 centimeters squared. So the first part says show that v equals a half r multiplied by, in brackets, 5,000 minus pi r squared. So first of all, we're gonna use the information given to us, and then so we're going to use the surface area. The surface area of an open cylinder, that means there's not a top circle. Let's just draw it out. The bottom circle does exist, and you know, has a base and stuff, but the top bit is open, so there's only one circle that will have an area. So the area of this is pi r squared. That's the area of the circle underneath, plus 2 pi r h, which is the circumference of the circle multiplied by the height. We want to find the height for this, so h equals 5,000 minus pi r squared all over 2 pi r So now, using this information, we can find the volume. The volume of a cylinder is pi r squared h, regardless of it being open or not. So we can just use our value of h that we just found. Oh, sorry. Yep. And all of this is over 2 pi r. Okay, and so from here we can just do a bit of algebra, I suppose. Well, first of all, I'll actually multiply the brackets out. So it's actually 5,000 pi r squared over 2 pi r minus pi squared r to the power of 4 over 2 pi r. And then you can start cancelling terms out. So let's get rid of this. This will be a cube now. This pi is going to just be a single power. This r can get rid of that, and this pi here. So equals 5,000 over 2 minus pi r cubed over 2. You can take, oh, there's another r here. Oh god, that was close. Yeah, you can take an r and a factor of half out, as shown in the question. So here's our result. Okay, the second question. It says calculate the maximum possible capacity of the bin. So what you want to do here, you want to find the volume in its expanded form. So let's do that. That's going to be 2,500 r minus pi r cubed over 2. Now to find the maximum radius, we want to do dv by dr. Okay, so that equals 2,500 minus 3 over 2 pi r squared. Now, at a maximum value, dv by dr equals 0. So, 2,500 equals 3 halves pi r squared. So r squared equals 5,000 over 3. Actually, 5,000 over 3 pi. R equals, I'll just calculate this quickly. That's 500. Oh, the square root of 5,000 over 3 pi. And that equals 23.0 centimeters. But it actually asks for the volume. So we use what our result over here to find this. So V equals 20, a half times by 23.0 multiplied by 5,000 minus pi 23 squared, 23.0 squared. Sorry about that, that is really not great handwriting there. And so let's just calculate that. Okay, alright, so the volume here is 38,388. So the volume of centimeters cubed, always can include your units. So that's approximately 38,000 centimeters cubed, and that's the maximum volume.